Hi, physics. Welcome back from your spring break, as it was. This is going to be what I call lesson 4.1. And with discussion with other physics students, it might be helpful if I actually did some presentations of my own. I've done this in chemistry already, but there are just some parts of this chapter which even the great videos that are on YouTube and the author does a good job of explaining it. There are just some things that maybe I want to make sure that you understand. So today's lesson for 4.1 will be about gravitational fields. This is in the book, section 9.6. There'll be other directions on Google Classroom besides just watching this YouTube video. But go ahead and get out your notes. What I have on the screen are similar, but not identical to your notes, but most of the information will be on there. And the drawings that I put on there, I took from the internet, but I'm going to be making some sketches of my own. So as we look at this, so look at gravitational fields. So right now the Earth is attracting you. You'll probably be in contact with the Earth, but you can also be attracted to the Earth without it being in contact while you're falling. Or if you're in space, you're still attracted to the Earth. The moon is still attracted to the sun. The sun is attracted to the Earth. All the different bodies in space are attracted to each other. And so can it happen? Can objects be attracted? Sure. Let me show you an example here. Here's a paper clip, and here's a magnet. And you can see it's not touching it, but there's a force between them. And in fact, do you see how the force is pointing toward it, even when I go at different angles? It's pointing toward the magnet, like that. Well, when it comes to forces, remember forces have direction and they have magnitude. They're vectors. And so I'm going to draw some vectors here. And so if I have the Earth and its center of gravity right there, there's my Earth, okay? And right here, there's a vector pointing toward it. Here, there's a vector pointing toward it. And you have something similar to this in your notes, but I'm going to add something else to it. See how these are about the same length? If I go further away, the vector is smaller. If I go a little further away, the vector is smaller yet. The forces decrease as I go farther and farther away. And you know how they decrease using the inverse square law. If you double the distance, it's 1/4. If you triple the distance, it's 1/9, and so on like that. So if something is here, it'll be accelerated with this force. If something is here, it'll be accelerated with that force, and so on. And as they get closer, you'll be accelerated more and more along. All these vectors combined together create what we call a force field. So if you're located anywhere in this force field, you'll be tugged in that direction. It's called a gravitational field. A magnet has an interesting field. Here's a magnet. I'm going to draw it over here. And we have a north and a south end. The magnetic field isn't all pointing towards the center. There are two poles, and the magnetic fields are like this. And then they curve around like this. Our Earth has a gravity field. So here's the Earth, and the arrow is pointing straight towards it like this. But our Earth also has a magnetic field besides, and it looks something like that. It actually helps us. The magnetic field helps to turn radiation away, harmful radiation away from us. And it kind of moves the radiation toward the poles, and it creates the northern and southern lights. Very interesting on that. There are some videos that I would like you to take a look at that are referenced in your notes. Make sure you take a look at that when you do that. So, but what I want to know is if we are inside a planet, what the gravitational field will be like. So what we're going to look at is going through a tunnel through the Earth. So I'm going to take a diagram here, and I don't think you have a copy of this, but I'd like you to imagine a tunnel through the Earth. If you want to make a sketch, I don't know if I gave you this or not, probably not. If you have a tunnel going through the Earth, and you were to start falling. Now we're going to assume there's a center of gravity right there. As you get closer and closer, you're going to fall faster and faster. And where will you be the fastest? Right here. You'll get faster and faster and faster. And then as you start going out this side, going this way, you'll start to slow down because you're being pulled toward the center, always towards the center, always towards the center. So as you start to go this way, you'll slow down. And you'll slow down just as much as you speed it up. And when you get right here, you'll stop. Now, if you happen to be right there at the edge of the hole and you grabbed on, you'll be okay. But if you don't grab on, you'll be pulled back this way again, getting faster and faster and faster. You'll get fastest right here, and then you'll slow down and slow down and slow down until you reach right here and you'll stop. Maybe somebody will grab you, but if not, you'll fall back down again. Now, you'll go all the way to the edge of the hole and all the way to the edge of the hole, back and forth forever. But we don't do that. You wouldn't do that because there is air friction. So what will happen is you'll go, start here, you'll get faster and faster, and you won't quite reach the other edge. And then you'll go back this way. You'll go a little less, and you go this way and a little less, and you go this way a little less, little less. You'll get slower and slower as you go past the center of the Earth. I don't know how many times, but you'll eventually stop right in the middle, and you'll just be hovering right there because the Earth is pulling you equally in all directions this way when you're at the center. You'll just be floating right there in the middle. Nope. That'd be kind of tough. It's about 3,000 miles to the center. It would be a long trip going around. It'd be about 90 minutes for you to go through the center of the Earth. That's assuming you survive all that. So there'll be a question that I'm going to have for you about what happens to you if you fall through a hole in the center of the Earth that opens to both ends. Now, obviously, they know that the center of the Earth is molten and hot, so that we wouldn't be able to do that. But what if we could go through in a solid form like that? Let's go through that again. You start out with 0 speed. You get faster and faster as you go towards the center. You'll be fastest right here at the center, and then you'll be starting to be pulled back towards the center, but it slows you down, and then you'll reach 0 again right there. If there was no air friction, you'd just be going back and forth and back and forth and back and forth. But because of air friction, you won't quite reach the other side, and you won't quite reach the other side, and back and forth like that. So I'm going to do one more little idea here. What if the Earth was hollow, like this, and we could go inside of it? Okay. Now, what would the gravity be like inside of this anywhere? Well, let's say I was right here. What's pulling on me is the outer edges of the Earth, if the Earth was hollow, and I am going to try this again. There we go. If you were right here, I'm going to draw a line across and a line across here. Now the closest part of the Earth right here is pulling on me, and the largest part of the Earth is pulling on me, is further away. Because of the difference in distance, this is a big distance and a lot of Earth. This is a little distance and a little bit of Earth. They cancel out. I would have equal gravity pulling me both ways. I would just hover right there. Now, it makes more sense if you talk about it being right in the center, because watch this. The amount of Earth that's pulling on me in this distance are the same as the amount of Earth pulling on me in the distance. So the gravities would be equal. So I would hover right in the center. But anywhere you are, even if you're close to this, look at this here. I've got a little bit of the Earth pulling me from a short distance, which makes it strong, but I've got a whole lot of Earth pulling me from a bigger distance, and they cancel out. That means I'm hovering. So inside of a hollow Earth, you would hover everywhere. The gravities would be equally pulling on you from all sides. See what the book says about that. There's a little picture there that Paul Hewitt wrote. All right, well, that's our first lesson on gravity fields, and there'll be a few questions that you'll need to answer about that.